Hello. Let's do a problem. We don't do much homework problems in class, so let's do one here on the video. At least you can see what it's like. So the book gives you a differential equation, it's second order, and it's got a forcing term. And it's got initial conditions, which means that we're going to be getting a specific solution at the end of this ride. Well, what's the first thing you have to do? Come on. Homogeneous solution. You just pretend that this is a big zero over here, and you work that through. It's not too bad. So you get the characteristic equation. Get the crumbs off the paper. Factors, which is nice. You didn't have to use quadratic formula. And this gives you the homogeneous solution, which is written here. And then I've underlined the hassle. The hassle. I spot, and you have to spot this yourself. I get an e to the 2t, and my forcing term has e to the 2t. So I'm in trouble, because I need an e to the 2t's to survive the differential equation. And according to this calculation, e to the 2t will always go to 0 in this differential equation. So we do the arbitrary constant, and I wrote this up, and I did a thing that I do myself all the time. I don't want to write subscripts. It's just so much work. So I used the letter A again. Oops, because I just used this letter capital A here. But this capital letter A is going to be replaced. It's like a temp. That's like a placeholder. It's going to be a number in just a few minutes. So I'm not going to worry about this. I'm just going to have to remember that this capital letter A is different from this capital letter A. That I won't see this capital letter A until the end of the problem when I do the initial conditions. I'll just not worry about it. I'm going to find a number for this spot. So I'm thinking of this as this spot. I'm going to get a number here. So I have to take derivatives. Some product rule derivatives. I got my like terms. Because this 2 is going to come down, I'm going to get a 2a e to the 2t. And then when I take the derivative of t over here, I'm going to get a 2a e to the 2t again. Like terms. When that happens, it's like a little emblem that, hey, you're doing it right, because that's what's supposed to happen. You're supposed to get a little repetition there. Let me get this out of the way so you can see the rest of it. It's all there. It's all there. I didn't lose it. All the pieces are there. I combined like terms for that second derivative, just because. You know, it's a bookkeeping thing. And now I take this all up here. Put those particular solution derivatives into the differential equation. So I have y double prime minus y prime minus 2y. And so I write them down. And I notice that, look at this. The t e to the 2t pieces happen to cancel out, which is what's supposed to happen, because I'm supposed to get a 9e to the 2t equals a times some other stuff, e to the 2t. And I do. I get a 3a e to the 2t equals 9 e to the 2t. I'm very happy. A turned out to be an integer, which means I'm probably on the right track. So now I've got my particular solution, which means at this stage of the game, and understand, at this stage of the game, I have the general solution. This is the general solution to any differential equation of this form without initial conditions. This differential equation up here, every solution is of this structure. Every solution. And then the capital A and the capital B depending on these guys. So what do we do from here? Well, obviously we use the initial conditions one at a time to determine these arbitrary constants, which we got from the homogeneous solution. So it's kind of weird, but this is the dance. Let's look through the dance again. Homogeneous solution. Arbitrary constants in front, we will find those last when we use the initial conditions. If we don't have initial conditions, we can't find them. Anyway, so we just leave them there. They're going to be done last anyway. Then we spot, do we have a hassle or not? Yeah, we got a hassle. So instead of just guessing y sub p equals some multiple of e to the 2t, I have to multiply by an additional factor of t, which gives me product rules, which expands my equation over here. But a beautiful thing happens. All the t e to the e2t's cancel, and I'm left with just 3a e to the 2t equals 9 e to the 2t, exactly what the doctor ordered. I get my particular solution. So particular solution plus homogeneous solution gives me general solution. And now we're going to solve for the specific solution. So all I've done is rewrite the general solution, and we're going to use y of 0 equals 0 first. Well, putting in a 0 for each t gives me a plus b equals 0, because y of 0 is 0, a times 1, b times 1, 3 times 0, it's gone. So a plus b equals 0. Save it. Now I got to take a derivative of this thing. I'm going to have a product rule right here. So I take the derivative. 2a e to the 2t minus b. Remember that minus comes from the derivative of that power. This 2 comes the derivative of that power. So I've got 2a e to the 2t minus b e to the negative t plus, product rule, 3 from the derivative of t, e to the 2t plus 6. The derivative of this power comes down, multiplies by that. This t survives. So I have a 6t e to the 2t. Now I do y prime of 0. All the t's go to 0. This term vaporizes. All the e to the 2t's and e to the negative t's become 1s. So I have a 2a minus b plus 3. That survives. And that's equal to y prime of 0. Y prime of 0 was known to be 3. That was our initial condition. So 2a minus b plus 3 equals 3. Subtract the 3's. 2a minus b equals 0. Bring down your a plus b equals 0. And these b's are ready to cancel by elimination. So I end up just adding 3a equals 0, a equals 0. Well, if a equals 0, then b has to be 0. Wow, well, that's kind of nice. My answer is just the particular solution. Y equals 3t e to the 2t. For this differential equation, the differential equation that started the problem. So this little skinny line of text right here generated this much work. 2 pages of work to get to, in this case, I did the dirty to you. And the particular solution was the actual solution. It doesn't work like that all the time at all. I fixed that up ahead of time. Okay, now I've got one warning problem to show you. And this one is quite, I don't know if I'd ever do this to you, but the book does. So if you do this in the homework, if you have the following situation, if you have, I'm going to use the same differential equation that we had before. So I'm going to have this differential equation that we just had. Let me get this down here. I'm going to have this differential equation, but I'm going to have, instead of 9e to the 2t, I'm going to have the y double prime minus y prime minus 2y. And remember what the homogeneous solution was. I have that e to the 2t and e to the negative t. Suppose I have t e to the 2t for my forcing term. Suppose I have that. Now let's look at why this is particularly thorny. You'd at first say, well, look, the homogeneous solution is e to the 2t. Well, this isn't e to the 2t, it's t e to the 2t. But it's made of a factor of a homogeneous solution. And because of what would have been the hassle was this factor isn't going to work properly. If, honest to God, if you guess y sub p equals just a t e to the 2t, it will fail. And not only that, you have to do the following. You have to guess this. For it to work, here's what you have to guess. You have to guess y sub p equals, oh my God, you won't believe it, a t squared plus b t e to the 2t. You have to guess all this much just to get the thing to work. Just to get it to work. Not just to, so you can't even just guess the regular guess. When you have a homogeneous factor matching, you still have to multiply by the t for the hassle. And here's what you have to think. This was a t. I have to multiply by, normally I would be multiplying by a t plus b. Because this is a 1-degree polynomial, I'd have to multiply by a generic 1-degree polynomial. And then I have to multiply that by t because of the hassle. So you have to take what would have been the guess and multiply by an additional factor of t. This is the only way to get the solution to this differential equation. Doesn't matter what the initial conditions are. If you have this kind of hassle, so factors can be hassles. That's the bottom line here, and you have to handle those. I'll leave you to try the rest of that one because I can do it. It takes a little while because you can see all these product rules that are going to happen, but it works. I guarantee you, it works. I don't know if I give you one of these on a test because, honest to God, it's 2 pages. It takes a lot of work, but the book gives them to you. So if you spot this in a homework problem, you want to get it right the first time, you have to multiply by this much. All right, see you later.